Wow, that's bad.
Okay, so we've just talked a little bit about what compound interest is and talked about a couple of examples.
We only talked about the sad.
So the video is going to show you just how to use the formula. This formula makes it so that you don't have to make a gigantic table and keep adding interest and interest and interest and interest. If you want to go every month for like 10 years, that would take a while. And so we've condensed it down into a formula. And there's lots of different pieces. Now the 8 would be the total amount at a particular time, which they're going to tell you. Okay? And so the P is your principal. Who can tell me what principal is?
It's the lady that runs the school. We suck. We get that.
Okay, so it's the original amount of money borrowed. So yes, it is spelled the same as principal, but it is the original amount of money borrowed or the original amount of money that you're putting into a savings account. It's just whatever you're starting with, okay? R is your interest rate, and a lot of times you'll hear that talked about as the APR. The annual percentage or annual percentage rate, okay? Okay, so then N is your payments per year. I should put number. It's the number of payments per year. So if you're paying monthly, that's 12. If you're paying annually, that's 1, which you wouldn't need compound interest then. If you're paying, well, I guess you could, because you could do several years at once with it. If you're paying quarterly, how many payments would that be? 4, because it's 4 quarters. Semi-annually, 2. So there's all these words that'll come up, and you'll have to figure out the payments per year.
Biennial.
Okay, so then T is your time in years. Okay, so the power that they're giving you up here on this formula with N and T is the number of total payments. So when you go and buy a vehicle, they always will tell you, oh, this will be, for me, if I was the one time I bought a new vehicle, I had to spread it over 5 years. It really stunk. And so there's like, okay, you're paying monthly for 5 years. That's 60 payments. And so this is just your total payments, because it's the number of payments per year times the years. So just so you know, that's what that power will be. And then the interest rate, I should point out that we're going to change it to a decimal when we work with it. So there's these little intricacies, but it's not going to be that bad, okay? Mostly it's just using a formula for this first part. And then I'm going to show you sort of a wicked formula in a little bit where we add as much interest as possible. Okay, so let's look at our first example. So we're being really optimistic here. You deposit $50,000 in an investment account, yay you. And it pays 6% annual interest, which is also, and you would only get that if you were investing a lot, I would think.
That's the same amount.
Okay, so in the first sentence, the 50,000, that's my principal, that's P. And the 6% is going to be my interest rate, R, except that we're going to change it to a decimal. What is 6% in decimal form? 0.06. So let's write that kind of out to the side. All right, and we're going to find the balance after 2 years. So that's my time, T. If the interest is compounded quarterly. So quarterly is 4 times a year. That means that N is 4. So we found all the numbers that we need. So our formula is A equals P 1 plus R over N to the NT power. So we're just going to put everything in. So the principal is 50,000. I'm going to have 1 plus my interest rate, which we said was 0.06 in decimal form. And then we're going to divide it by the number of times you're paying per year. So this is your annual percent interest, but then they're going to divide it up over how many payments you're going to pay. So since we're making 4 payments, they're going to divide that by 4.
I feel like this is a lot better than Gibson did.
Okay? And then in the power, what we're going to do is we're going to take 4 times 2. So this is 4, and that's 2. We're going to multiply that, and that gives me the total number of payments is 8. So that's our total payments that we're going to make. Okay? And so what this is doing is basically it's adding on the interest 8 times, but it's using a power to do it so that you don't have to keep calculating. And you could literally type this whole thing into your calculator. Just make sure that you use parentheses And then we round it off to the nearest penny, which comes out $56,324.63. Okay? So that would be the total if you type all of this in. But you want to make sure you do the 4 times 2 first and just have 8. Otherwise, you could put 4 times 2 in parentheses. But this is just your total payments. So kind of what's happening is they're taking that annual interest rate, the APR, dividing it by how many payments you're making in a year. So it's sort of dividing the interest up. And then the power up here is basically it's doing those repeated multiplications for you. We're using the power so that we can do it in one step. Otherwise, you'd have to make a table and keep adding on that 6% divided by 4, and you'd have to have like 4. Actually, it would be 4 payments per year. So yeah, it's just you just would go on for a very long time. You'd have eight different parts of your table that you'd have to add that onto. And we have done this before, but we did the big table and we used the calculators, and it took a long time with the big table. You probably remember freshman year. This is a shortcut because we're using exponential stuff. And later on in this unit, I'm going to teach you how to solve for the interest rate and how to solve for the time. And we'll do more with this equation after we learn some things about logarithms. Okay, so let's do another example for this, and then I'll switch gears a little bit. So you deposit $15,000. I made these just so they'd be fun. We pretend we have money. So that's our principal. In an investment account that pays 4% interest. So that's my interest rate. Let's change it to a decimal, so 0.04. Find the balance after 5 years. There's T. If the interest is compounded monthly. So monthly means how many times a year? 12. So N is going to be 12.
Except on leap year.
So when we set this up, we're going to have 15,000. And then we'll have 1 plus the interest rate, which is 0.04, divided by the number of payments you're going to make in a year. So they're taking that percentage and dividing it by 12. Okay? And then up here, we're going to have the total number of payments. So it's 12 payments a year times 5. So 12 times 5 is 60. That's going to actually be my power. And then this is what you can type into your calculator. Some people like to do this part first, but you get a weird repeating decimal. So I'd say just type it all in, use the parentheses, and it comes out $18,314.95. So this is just compound interest. If you were putting something into an account and you knew how often they were adding interest, but this also works if you are, say, you've got something on a credit card, you could figure out interest over time. Then you also have to factor in if you're making payments, though. So there's a little subtraction that would have to go on there. But in general, that's how the compound interest formula works. Now, we're going to get a little mathy, a little bit away from the real world. Somebody sat, and just give me a second. So somebody sat and go, okay, so I could add interest, twice a year, or quarterly is 4 times a year, monthly is 12 times a year. And what if I did it daily? That'd be 365, or like leap years, 366. But then they kind of went out and started going, well, what if I did it twice a day? What if I did it every hour of every day? And they made it this table, and they found out that it sort of like levels off, and there is a limit to how much interest you could charge. And that's where we're going to get this next part. So we're going to start by introducing the natural base E. E is kind of like pi. So the number E, it's like a little cursive, italic, something E. It's called the natural base E, which is in the title, or the Euler number, which is spelled E-U-L-E-R. It's named for a German mathematician. It's supposed to be spelled Euler. I've heard people pronounce it Euler, but I was told in German it's Euler. I don't speak German, so I really don't know. Okay, so the natural base E is. So I want to show you where this is on your calculator. Okay, on your calculator, above your division symbol right there, there's an E. So if you hit the second key, and then that button with the E, which is your division sign, and just have that on your calculator and hit enter, it's going to give you this weird irrational number. So this decimal technically goes on forever and ever like pi does. It never stops, it never terminates, but this is the limit for this particular number E. So we're going to write down part of this, 2.71828 1, 8, 2, 8, and then after that, it doesn't have as many 2s and 8s, and I promise it starts getting really irrational looking. And so that's really what this is supposed to be down here. They're the same thing. Okay, so if we're wanting to round it off, most of the time if you did 2.72, that's about equal to it. So I think that's what's supposed to go here. Base E functions are used a lot in biology, which we'll see later in this unit. And we sometimes use them in population.
Wait, are we doing biology and math?
Population growth. And it's also used for economic growth. And what we're going to use it for today is for continually compounded interest. Okay, so we're going to use E for a lot of things. This is just the lesson I introduce it. What we're going to use it for today is what if we could infinitely collect interest? Someone was trying to get rich. I don't know. And so like if we were charging the most interest possible and infinitely compounding it, we get this formula down here, which I've already filled in for you for... So it's, yeah, I call this the PERT formula, P times E to the RT. So P is the principal, just like it was before. R is your interest rate. So really the variables, and that's your APR.
And T is time.
And then T is time in years. Okay? So it's actually a simpler formula because this is just like the most interest you could ever get if we compounded it infinitely often. I don't know who thought of this, but they were like, so how much interest could I theoretically charge? Can I ever get this much money? And they figured there's actually a limit to how much you can get. And this is how they do it. It's with an E. Okay? So it says if you deposit $1 million in a savings account, so again, trying to be optimistic here, at 7% interest compounded continuously, what's the balance after 5 years? So here's my principal. My interest rate is 7%, so that'd be 0.07. It's R. And then the 5 years is my time. So your formula is P times E to the RT power. So the principal is 1 million. And then E is just E. We're going to use that on the calculator. And on the RT part, what we're going to do is we're going to take 0.07 times 5. So you might want to do that part first. Or if you're typing this in the calculator, I'll show you how you can do it all in one step. Because I know some of you like to make this as simple as possible. So you're going to put in your 1 million. Oh, there's another E button on the left-hand side, by the way. Over here, there's an E to the X key. So let's use that one just so you see what it is. If you need to put a power on E, do that one and it'll automatically set up your power. And on yours, I think it might give you parentheses. Does it give you parentheses? No.
Yeah.
If not, then make
It
may depend on your calculator.
Mine is not paying attention.
Okay, so what you're going to type in actually is going to look like this, and you'll have E to the parentheses 0.07 times 5. That's how you want to type it in. And so I'm going to do that on my calculator. And I just got $1,419,067, and it rounds off to 55 cents. So I made this positive. We're pretending that you had $1 million to invest. But this formula would also work if you were doing continuously compounded interest for money that you're borrowing or whatever. Okay? It's more of a